So I'm going to talk about large-scale DFT. This really is the heart of what I do. Maybe 25 years ago, I was there at the beginning of the linear scaling kind of ideas, and 25 years ago, everybody had their own linear scaling method, and then very, very rapidly, the number of people working on linear scaling DFT shrank, because it turned out to be quite tricky, quite difficult to do anything useful with it. And now I think we're getting to a stage where actually large-scale and linear scaling DFT is quite mature, and we just need to encourage people to use it. And we'll talk a little bit more about this in a minute. So let's start by asking the question, what is large scale? For me, large scale means somewhere between 500 and 10,000 atoms. About 18 months, maybe 2 years ago, I did an informal Twitter poll. I got about 150 responses. I asked people who did DFT how many atoms they used in their calculations. And let me just check the numbers here. So 55% of those people used fewer than 100 atoms in their calculations. And only 4% went as far as 1,000 atoms. Okay. Now, I think if you'd done the same informal poll 10 years ago or 20 years ago, the numbers would not have been very different. Okay, and to me, this is actually quite shocking, given how much computational power has changed, how much we've done in terms of development. The fact is that we really do need to encourage people to change their practice. And so we need to be thinking about large-scale calculations. For me, I always think in terms of the number of atoms per process. And I will say process, not processor, not core, because you can break things up in different ways. And I think in terms of MPI processes. But roughly speaking, I tend to think of doing somewhere between 5 and 50 atoms per process. And I will typically use between 100 and 1,000 processes. Though if I'm doing some coding on my laptop on the train, maybe I'll dial that down just a little bit. Even the latest machines don't go quite that far. And if you want to go beyond somewhere between 1,000 and 10,000 atoms, then you need to think about linear scaling methods. If you can go to many atoms, that enables you to go to large length scales. Though remember that if you're wanting to talk about the whole volume of the system, of course, if you want to make the volume twice as big, you have to use 10 times as many atoms. So that's always going to kill us. If you can go to many processes, then you can reduce the number of atoms per process, and you should be able to go to longer timescales because the time per MD step or the time per self-consistent cycle should reduce. And a question that I'm going to come back to in a moment, which a number of people here have already asked me, is why are so many DFT calculations so small? Okay, why does everybody keep using cubic scaling? But maybe I think really it's just habit, and I'll talk more about that in a moment. We have become, as a community, very, very good at doing any calculation we want with about 250 atoms. Okay, any problem you think of, we can chop it down, compress it in, and you can do it with DFT with 200 atoms. But there are many situations where you need to go to larger scale. Dislocations and surfaces. I have a feeling that Vikram's going to mention this because he was talking about this to me the other day. Amorphous and heterogeneous materials, any kind of realistic concentration. So my favorite example here, which you probably have all heard me say before, is the metal insulator transition in silicon. Okay, so if you want to do that as an experimentalist, that's 10 to the 19 dopants per cubic centimeter. So if your doping is higher than that, you now have metallic silicon. And that's what people who grow semiconductor devices use to make semiconductor devices conduct. But 10 to the 19 dopants per cubic centimeter is one dopant per 50,000 silicon atoms. So I think we could say that every single DFT calculation of a doped semiconductor that has ever been done is categorically wrong. Okay, because I mean, you can fiddle it, you can make it spin polarized, and you can stop it being metallic if you want to, yes, but the dopant wave functions will be overlapping and you will have band states. You can also look at concentrations in seawater. This is something I stole from another person who works in the field. So saline solution that people put into hospitals, you need at least 1,000 atoms to get that level of concentration right. If you want to go to seawater, you need around about 1,000 atoms. So concentrations really are important. Biomolecules are huge. and Heather Kulik, among others, who spoke on Monday, has shown that you need a minimum of 500 atoms in your QM region if you're doing QMMM before truncation stops affecting the center of your QM region. And something that I put on because of what we've been hearing here, neural network potentials are all very well and very fine, but how do you know that the potential that you fitted to a small calculation scales well to a big calculation? You need large-scale DFT. Of course you need large-scale DFT. I'm always going to say this. Just an example here of why it's also really good to cross-fertilize. So this is a series of calculations done by an experimental colleague of mine. So he's a Japanese experimentalist. We've worked together on STM of silicon surfaces. He wanted to come and learn to do DFT. So the first thing he did was just take simple silicon 001 surface, and he wanted to reproduce the density of states, the tunneling spectrum that he got in experiment. And on the left-hand side here, you can see how many layers we've got in the calculation. At the bottom here is 6 layers, which people, by the way, still publish today, 6-layer slabs, going 6, 14, 22, 30, 62, 78. You only converge the gap, which is here, when you get to at least 60 layers of silicon. Okay, so the smallest silicon cell that you can do needs at least 250 atoms in order to get somewhere near the correct gap, and you're still imposing a kind of a quantum well state on the thickness of your slab there. This is a slide I put in after some conversations here. Why not? Why don't people do big calculations? I keep hearing the thing of, what's your killer application? You know, what's the one thing that will convince us all to do large-scale DFT? Well, there are lots of applications, but people just don't seem to kind of take that into their general everyday practice. I think there's a lot of received wisdom and habit. I find that undergraduates that I give my code to will regularly break the machine because they assume they can do thousands of atoms. Okay, you know, established DFT practitioner, you say, I want to do this calculation. They say, oh, well, we can't go much beyond about 200 atoms there. Let's figure out how to truncate it down. What do we do? People sometimes think that big is hard, but actually there's a bunch of codes now where big is easy. The only thing that actually might be difficult is data analysis. You know, when you've got 10,000 atoms, there's an awful lot more going on in your results. You could call this one the VASP effect if you want. Everybody uses VASP, or other codes which are available. You get comfortable, you get familiar with a workflow. I think originally one of the huge advantages VASP had was its library of pseudopotentials. Okay, when I started my PhD, people would kind of sidle up to you at a conference and say, have you got a good pseudopotential for silicon? Well, no, everyone had a pseudopotential for silicon, but, you know, they would pass around pseudopotentials that had been well tested. And then VASP came along with this big library, and you could use it, and you could plug it in, and they'd already set the plane cutoffs for you, so you didn't even have to think. Okay, though, of course, quite rightly, they do say test your pseudopotentials, and you always should. But there is now this inbuilt familiarity of how we do things. There's also, I think, an underestimation. We don't realize what errors we're introducing. So this is why not, but what I'm going to say is you can and you should. We should, as a community. When you're doing a large-scale calculation, well, any calculation, you have to think about competing requirements. You've got accuracy and you've got cost. Okay, and these things are going to depend. So, you know, the system size will, of course, affect accuracy, and boy, will it affect the cost. The functional, the time you run your MD for, the type of solver you use, these are all things that we've got to play with in our minds. Of course, pseudopotentials will come into this as well. And there's this question of how many atoms. You can go between efficiency, where you've got few atoms and you represent the problem. You can go to accuracy, where you've got many atoms and it's realistic. And then you sort of move between the perfect crystal and defects and dislocations and interesting problems. And of course, if you were to take this scale all the way out that way, then you'd end up with the kind of things we were hearing about last night when you're modeling dislocation dynamics, which you don't want to do with DFT. So how do we find the ground state, and what kind of scaling is there? Obviously, the standard approaches are n-cubed, and generally that divides into either direct diagonalisation, take the Hamiltonian, dump it into Scale APAC or LAPAC, get the answers, or variational solvers where the orthogonalization is what kills you. PEXI is one of the examples, the best known example of an n-squared solver, though of course the scaling for PEXI depends on the dimensionality of the problem. But a 3D problem gives you n-squared scaling. And then you've got linear scaling, where you're imposing a localization on the density matrix, and roughly speaking, you can divide that into iterative methods, which is the kind of thing that Anders described, this SP2 method, variational, which I'll describe in a minute, and then patching or subsystem methods, which is what Nakano-sensei talked about. Yes, hi, Anders. Yes, you're absolutely right. Stochastic methods is one I've missed off. Thank you. You're quite right. So this is patching and subsystem is divide and conquer, and then there is this group of stochastic methods where you pull random numbers out and you kind of try and converge the errors. Here's another reason why we need to do large-scale DFT. I think most people here are invested in the idea of exascale and big computing centers, and we need to provide use cases. So we've got HPC centers with hundreds of thousands of cores, and we must do good parallel scaling. We need to make sure that we go down to the ground state efficiently, and we need to think about system size and communication. And nowadays we have to think about not just CPU, CPU, but CPU, GPU, and even GPU, GPU communications. And then even using GPUs, and recently you have to think about multi-threading versus message passing, you have to think about heterogeneous architectures. But all of these things can be used to do large-scale DFT. And these are all driving what we're doing. So here are some examples of large-scale DFT calculations for various different codes. Of course, CONQUEST is at the top because that's my code. But we've got a number of codes now which have definitely demonstrated you can go to millions of atoms. You've got codes which have definitely gone over tens of thousands of atoms, and all of these calculations here are linear scaling. The bottom two here are exact diagonalisation or cubic scaling calculations. So RSDFT is a Japanese code, and they did 107,000 atoms on the entire K computer. And Google recently have been working on using their tensor processing units. They did 31,000 atoms, but these were all electron calculations, and so it was more like 200,000 orbitals. So of course there's a question there. Volker was involved in doing some of this work, so if you want to know more about that, then do ask him, not me, because I didn't. And then here's the flip side. How many processes, how many cores can you go to? And here's an example of the number of the scaling that people have gone to. This DGDFT, that was actually announced at the Supercomputing Conference last year. It's a Chinese code, and it was running on the Tianhe, the Sunway, their new machine. They went to 36 million cores. CONQUEST has gone to several hundred thousand cores, MGMOL has gone to 1 million cores, and the various other codes scale well. Real space DFT, that also scaled to 600,000 cores on the K computer. So what this is designed to show you is that it is now perfectly possible to go to very large system sizes and very large computers and do these real calculations. So let me now tell you about CONQUEST, which is our code, and how we use this. The key idea behind all of linear scaling and large-scale DFT is real space locality. It enables both good scaling in terms of number of atoms and also parallel efficiency. Okay, so you get a win-win situation. Whereas standard DFT implementations are non-local, so the wave functions span the entire system. If you use a plane wave basis, they of course span the entire simulation cell. But we know that electronic structure is local. Okay, so the charge density, which is at the heart of Kohn-Sham DFT, is local. Vanier functions are localized. The density matrix is known to decay. The form of the decay depends on the system, and everything I'm going to be talking about from here on in is an insulator or a semiconductor. So I'm talking about gapped systems, and in gapped systems, the density matrix decays exponentially with distance. Okay, so we should be able to use this. And in CONQUEST, what we do is we use local basis functions, so those are key. They give you sparse matrices, which again reduces the scaling, reduces the memory use. It also means that almost all of the operations are local to the process that's managing the atom. So we reduce communications. That improves efficiency. It then naturally fits with Walter Kohn's near-sighted principle, which is what I was just talking about, the fact that electronic structure is local. And it makes parallelization simpler. There is a cost. So if you have localized basis functions that move with the atoms, that gives you Poulet forces, but you can calculate those. Do you orthogonalize your local basis functions, or do you work with an overlap matrix? That's still an interesting question. How do you systematically converge localized basis sets? I'll talk about that later. And just to set the terminology here, the Kohn-Sham basis psi nk of r is expanded in a set of local basis functions phi I alpha, which we call support functions, multiplied by some coefficient. This is a fairly standard kind of thing, but I just wanted to introduce the idea of these support functions. These support functions themselves can then be represented in terms of another basis. So you'd write phi I alpha of r as a sum over something s of chi s of r. And these basis functions we can do two. We can either use pseudoatomic orbitals, the standard kind of thing that you see from siesta, where you take a spherical harmonic and multiply it by a radial function, or we can use a systematically convergent basis set. We use B-splines or blips, and you get other things. So big DFT uses wavelets, 1TEP uses sinks, periodic sync functions, and there are various other ways that you can do that. PAOs are nice because you can do the spherical harmonic integrations analytically, and that just means it's a 1D problem for doing integration. It's a small basis and it's relatively intuitive. The blips are systematic, so you just change the spacing of the grid that they're defined on, and that converges the energy in the same way that a plane wave calculation will converge. Mostly at the moment we use PAOs because they're easier, but we have the blips available. How do we solve the density matrix? So we don't actually, most of what we do doesn't involve the wave functions, it just involves the density matrix. Once we've calculated the support functions, once we've calculated the matrices, the Hamiltonian and the overlap, which is done in a linear scaling way, we either diagonalize using scale APAC, and we do that up to about 10,000 atoms, or we use an order n solver where we go from somewhere between 1,000 and 1,000,000 atoms and beyond if we have a big enough machine. And the nice thing is that this is complementary, so you can choose the appropriate method. You've got the same basis functions, you've got the same Hamiltonian, you've got the same everything. It's just how you're getting to the ground state that changes. And we want to have efficient, accurate solutions for any system size on any machine that we run on. Just a note that when we diagonalize, we don't actually store the wave functions. What we do is we build the density matrix. So if the wave functions are defined like this, then the density matrix is defined like this. So when we actually do the exact diagonalization, rather than storing the wave functions, we store density matrix, and that's actually really efficient in terms of memory use. It pulls down the memory use compared to everything else, and it means that you're folding all of the Brillouin zone sampling into this sum. That's just a brief note. So what are the basic capabilities of CONQUEST? We have efficient parallelization. You can run it on one core. You can run it on a laptop quite effectively. We've gone to over 200,000 cores. You can go from a single atom to over 2 million. The forces are exact and analytic. We've done MD with linear scaling on 32,000 atoms. I'll tell you a bit about the pseudopotentials in a minute. We've got a number of functionals. We interface to libxc, and it's open source. It's available under the MIT license, so anybody can go and take it and use it and change it as they wish. And personally, I would encourage you to go and play with it and see what you can do. And just to show you the scaling, this is data from the K computer, where we're changing the number of atoms per core, or per process, if you like. So this is 32 atoms per process going all the way down to 4 atoms per process, and then we're changing the number of atoms. And there are two things I want you to take from this graph. First of all, down here, so that's 4 atoms per core, so that's the 200,000 core calculation. And over here is the million atoms, but notice we're changing the system size, and the time per process is completely flat. Okay, so as we increase the system size, we get perfect linear scaling. This is all done in terms of weak scaling, where we're keeping the load per process the same, but it scales very, very nicely. And if you look at how it changes from 32 atoms per core to 16 to 8 to 4, you'll see that it's not quite as good, but it's still not bad. So up here we're at about 17, we go down to about 9, we go down to about 5, so it's not quite halving, but it's awfully close. And obviously, as you get down to a smaller workload, so once you go to 4 atoms per core, then that reduction gets worse. So the strong scaling isn't quite as good as the weak scaling, but the weak scaling is essentially perfect, up to 200,000 cores. How do we parallelize? Roughly speaking, we assign areas of space to MPI processes. But the way that we do this is using a space filling curve. So we divide space up into little blocks, we put a Hilbert curve, a space filling curve through those blocks, and then we unzip it. Okay, so you're mapping the 3D space into a 1D space, and then we just chop up that one-dimensional line so that you've got the same number of atoms in each segment, and those are then assigned to different processes, and we then try and assign the same areas of the integration grid to the areas where the atoms are to reduce communications. So that's roughly speaking all I'm going to say. So let me tell you a little bit about the basis. Any questions, by the way, before I go on?
Dave, you mentioned that DFT, FP, and parsec were linear scaling, but I think that's not the case.
That's a very good point. Yes, I probably put them on the wrong part of the screen. Yes, they are. They're not linear scaling. Yeah.
Sometimes there's a difference also in memory treatment.
Yes.
Maybe operationally.
Yep.
Linear scaling, but quadratic in memory.
So that's a really important point. So, and if you couldn't hear that, Anders is talking about the difference in memory scaling against operation scaling. With CONQUEST, we worked very hard to make sure that all of the memory storage is linear scaling as far as we possibly can. Obviously, when you're doing exact diagonalisation, you have to store the full matrix, and that's n squared. Everything else is linear scaling. But that's a very good point. And quite often we find that we're memory bound. Yeah.
Following the same line with Vikram, I don't think DGDFT is linear scaling either.
Okay, I'm going to sit down with you guys and change my slides later.
and that 2.5 million
yes.
atom calculation was Paxi calculation for metal.
Okay. All right, thank you. I really should check these things very, very carefully before I talk to this kind of audience, because I know there are going to be people who'll pick me up. Anything else I've got wrong? I think it's really important that people can pick you up when things go wrong, and I think it's important at any level. I mean, when I'm teaching undergraduates, I make mistakes, and I think it's really important to acknowledge that and tell them, yes, absolutely, well done, you got me. So thank you. So pseudoatomic orbitals. We use the pseudodojo pseudopotentials. I'll show you that in a minute. And the question that I had in the back of my mind was, can we define reasonable default basis sets for these pseudoatomic orbitals? Because the way that they're defined is typically you have the valence electrons, you add in polarization orbitals, in other words, you go to the next level of angular momentum, and then you have a number of radial functions for each angular momentum channel. And so how do you know what's reliable? How do you define sensible basis sets? So you've got the question of how many radial functions you want, the question of how many angular momentum channels you've got, and then how do you define the radii? Okay, so you said you've got different radii. How do you take all of these different ideas and make something sensible? What I'm going to show you is, I'm not claiming that this is absolutely reliable, but I think it's reasonable. So what we've done is we've defined two radii. We've got a very, very small radius, which is equivalent to a 2 eV shift of an orbital. So you take an atomic orbital and you squeeze it really hard, and the energy jumps by 2 eV, and that gives you a nice, really compressed orbital. You then have a 20 MeV shift, so that's hardly changed at all from the free atom, and you use those two as your limits on the radii. And that allows you to define very easily basis sets from single zeta up to triple polarization. And so we sort of have these default basis sets that the user can just push the button on, though of course it always comes with the warning that you need to test your basis set. Just to show you, this is the table from the delta function study, which I think is still the single nerdiest science paper ever published, and it was done by our community, which is brilliant. And just to show you that actually the ONCV-PSP, which is this Don-Hamann pseudopotential, which is norm-conserving, down here, it has as good accuracy compared to all-electron calculations as most of the all-electron calculations themselves. They're an incredibly good set of pseudopotentials. They are also quite a heavy set of pseudopotentials. They have a lot of valence states and semi-core states. So we do want to look into a slightly lighter set of pseudopotentials, but they're there and they're reliable. So we've got a code that generates the PAOs for you, but allows you also to take full control and make your own basis sets if you want. Yes?
The previous table.
Yeah.
So at the bottom, why the same ONCV? When you put them into quantum espresso, the error seems to be different.
That's a really interesting question. It's different. So they are a subtly different set of pseudopotentials. So you see that this is SG15.
Yeah, that's
So that's the François-Gigi set, whereas this set are the pseudo-dojo set. So ONCV-PSP is the kind of the background philosophy and the code. And then the pseudo-dojo versus the SG15 is the sort of the library of pseudopotentials that people have published. So basically the pseudo-dojo is a bit more accurate than the SG15. Quite a bit more accurate, yeah. So, but I don't have any insight into why that is. So let me show you some results. So these are tests of triple zeta, triple polarization in the table. So that's the full big basis set versus quantum espresso using the same pseudopotentials. Okay, so there's no difference in the pseudopotentials. It's all the same. And there's lots of numbers here, but basically what you should be able to see is that the plane wave numbers and the PAO numbers are essentially the same. And you can see on this graph that actually as you go from, not surprisingly, a single zeta polarization basis set is useless, but actually going to DZP and TZTP reproduces the binding energy curve of bulk germanium very nicely. And I can go through a bunch of different things here. So this is Stishovite, and you can see here that comparing to VASP, which is using a completely different set of pseudopotentials, we can converge to essentially the same number. And you can see how these things converge as you change the basis set size. So, we wouldn't recommend using single zeta. You can use single zeta polarization if you really need to go quickly, but actually DZP or TZTP is very, very good match to fully converged plane wave results. Okay, so all of these plane wave results, they're not the kind of the getting away with it level, they're at the fully converged level. Yes, Volker?
Do you know anything about how well VASP is converged? So this isn't picking on VASP, but actually the oxygen pseudopotential in general.
Okay, I don't know. So this was done by somebody else. But the fact that we got pretty similar results with two different sets of pseudopotentials suggests that things are fairly well converged. But I mean, in terms of plane wave cutoff, the VASP had been taken to the hard limit. Okay, yeah. I'm sorry, I don't know. And this is just to show you again. These are boring. This one is slightly more interesting. So this is one of my PhD students, and you'll see quite a lot of his work from here on. This is looking at lead titanate, so PbTi03, which is a perovskite. And Jack was interested in the ferroelectric properties of PTO. So the question he wanted to know was, how good is the density, the charge density that we're getting out of the PAOs? And so he took, I think it was Abinit, it might have been quantum espresso, but again, same pseudopotentials. And what we're wanting to do is to compare the charge density to the completely converged 40 Hartree cutoff plane wave result. And he's plotting this either in the lead oxygen plane or in the TiO2 plane. And you see that, again, not surprisingly, the single zeta polarization isn't very good. And then as you increase the basis set size, it becomes really very good indeed. Though interestingly, even the SZP is really only near the center of the oxygen that the charge density differs significantly. And that's quite a useful thing to know when you're doing things like polarization in ferroelectrics, because charge density really does matter. So this was nice, and then he turned this into a kind of a convergence graph where he did a whole series of plane wave calculations, and he looked at sort of the difference in the total charge density for a series of plane wave calculations going all the way up to 40, and also the total energy per atom in the same way, and then mapped the CONQUEST results onto this. And what that showed was that even an SZP calculation was actually equivalent to about a 20 Hartree plane wave calculation, and this TZTP was going up towards a 30 Hartree cutoff. So it's just demonstrating that these are actually reasonably accurate, which is reassuring. Let me tell you, I've gone too slowly. I'm going to have to speed up. So multi-site support functions, this is the way that we're bridging between the relatively small 1,000 atom calculations and the reasonable 10,000 atom calculations, but all still done with exact diagonalisation. Okay? And so essentially what we're wanting to do is have an accurate basis set, but efficient performance. And so what we're going to do is we're going to shrink down the set of support functions for each atom to essentially to the same number as a minimal basis, but we're going to keep that as being a large and accurate basis set. And so the way that we do this is that we allow the support functions to expand and bring in basis functions from a whole bunch of atoms around. So they're effectively a set of local molecular orbitals, if you like to think of it in that way. And so the advantage of this is that it reduces the Hamiltonian size. Okay, so for something like silicon, where you would have a big basis set with 27 orbitals, you can reduce the basis size down to 4 orbitals per atom. Okay, so that's a reduction of like about a factor of 7, which means it should go about 300 times faster in the diagonalizer. And the intention is to find that we don't sacrifice accuracy. And so this is just a plot here showing that as you increase the radius of the support functions, the energy deviation, and this is a log scale on the y-axis, comes very, very quickly down towards 10 to the minus 5 eV per atom. The two curves, one is silicon, one is aluminum. I say aluminum because I'm in America. If I was in the UK, I would say aluminium. But they converge at about the same rate. And it's a really nice idea. It comes from Mark Grayson and Patrick Bridden, who work on the AIM Pro code in the UK. We've made various improvements to it, and I can tell you more about it if you're interested. But fundamentally what we do is we define an orbital radius. We take all of the local functions to the different atoms and then create these larger but smaller number of functions. I'm not going to show you that. You can also then, so that this is a technical detail, the way that we do it normally is we create a small Hamiltonian, we diagonalize, and that gives us the basis functions, but you could then optimize and improve the representation. And the nice thing here, so this graph shows you the binding energy curve for silicon. These black triangles are for quite a small radius. And then when you come down to these open triangles, this is what happens when you optimize. So you see that for a small radius support function, you can improve the total energy and the lattice constant dramatically. So that was for a sort of a 5 Bohr radius. The squares are for an 8 Bohr radius. The circles are for a 17 Bohr radius, and the x's are for the full basis set. So you see that we converge very rapidly, and we can improve things that way. And this is a slide I want to go through just a little bit slowly, because I have to stop and apologize to my Japanese colleagues. So when they first wanted to implement this, I said, I don't really see why we should bother. Okay, I'm happy to say that. I said, you guys want to do this, that's fine, but I don't really think it's going to give us much advantage. So let me talk you through this. So first of all, this is for graphene on rhodium-111, and these first two columns are for 1,500 atoms. And what you see is that with just pure PAOs, you've got 27,000 support functions. Using these multi-site support functions, you can reduce that by about a factor of 3 to 8,000 support functions. We're running on 432 MPI processes, and the PAO total time is 1,200 seconds to get to the ground state. The multi-sites, it's 400 seconds. Okay, so there's a saving of about a factor of 3. That's quite nice. Now let's think about what happens if we go to a larger system. So this now is contrasting two full PAO calculations with either 1,500 atoms or 3,000 atoms. So we double the number of support functions. I still haven't got to the bottom of why they reduced the number of MPI processes. It was something to do with node loading and total memory, but it makes the numbers worse, so I apologize. This is the interesting point. The diagonalization has gone up by a factor of 32,000. That's because you get a factor of 4 from a factor of 8 from doubling the number of atoms, and a factor of 4 from the number of MPI processes. Okay, so that makes sense. We've gone from 1,200 seconds to 37,000 seconds. So long calculation. Now, contrast the same 3,000 atom calculation with PAOs and multi-site support functions. And here's the headline figure down here at the bottom. We've gone from 37,000 seconds to 2,000. So we've reduced the total time by a factor of about 16. Okay, that's enormously improved and is a really very nice kind of improvement and speed up, and allows us to do 3,000 atom calculations in very, very quick times. But then the final one, this is the thing that I really like. Going from 1,500 atoms to 3,000 atoms, from 432 MPI to 864 MPI, so we've doubled the number of atoms, we've doubled the number of processes. Look at the time to the ground state. It's basically the same. So we almost got linear scaling with exact diagonalization. Okay, now we haven't, of course we haven't. What we've done is we've reduced the diagonalization time to such a small amount that it's kind of hidden. But it's just really nice illustration of how you can play games and you can really push and improve performance. And when I saw this, I said, you were absolutely right to implement this, and we now use this. And this is a very, very nice piece of development. I'm going to have to speed up just briefly to show you some applications of these multisites. Again, coming back to these ferroelectrics, lead titanate on strontium titanate. And we're looking at and we're interested in this layer, which is the lead titanate, and we're wanting to look at what's happening in that layer in terms of ferroelectricity. So what's the local polarization doing in this system? I'm not going to talk about that. I'll just show you this picture because it's a pretty picture. This is a plot of the local polarization vectors in the PTO film with 9 formula units, and this is a thinner film with only 3 formula units. And what we found is that you get proper flux closure domains, and so you can see a domain wall here and a domain wall here. Sorry, the domain walls are here and here between these domains of different directions of polarization in the film when it's thick. When it's thin, you can't support that, and you end up instead with this kind of wave going across the thin film. And this maps into experiments where they're trying to look at the kind of polarization textures you get in these kinds of films. And I can't show you the full details, but actually you also end up with a competition between the ferroelectric distortion and anti-ferrodistortive rotations of the titania octahedra. These are other things that we've looked at. We've looked at nanowires, and we've also looked at, I showed you the graphene on rhodium. This is yttrium, gallium oxide, and these are metallic nanoparticles. These are all things that we're using. We're doing practical calculations with somewhere between 3,000 and 10,000 atoms with exact diagonalization. So I would say that a number of these are effectively killer apps for big DFT, for large-scale DFT. Let me tell you very briefly about linear scaling, because that's where you get to really, really big system sizes. So here's the key idea. Oopsie. So we've defined the density matrix. This is the formal definition, but of course, if you're doing linear scaling, you don't do this. So the formal definition is like this, but we know that the density matrix is ranged. It goes to 0 as the distance between 2 points in space increases. And so the key idea in linear scaling theory is to impose a cutoff. Okay, so we just force it to be 0 once you've gone to more than a certain distance between points. We can't, of course, work with a full 6-dimensional function. So what we do is we represent it in terms of a matrix, ki alpha j beta, and the support functions that I've already introduced. And then in order to find the ground state, you have to minimize the total energy with respect to both the support functions and the density matrix. And then as is standard, you maintain the direct electron number, you maintain cell consistency, and here we maintain idempotency. So the normal DFT code, you would maintain orthogonalization between the orbitals, and you would make sure that the occupation number was 1 or 0. Here we just go for idempotency of the density matrix. And this is the thing that's hard to impose. And we truncate in 2 ways. First of all, the support functions, which are confined within a sphere. We then truncate the density matrix in this way. So once 2 atoms, I and J, are more than a certain distance apart, we just force it to 0. That's all we do. And I'll mention in a moment that there are other ways of doing truncation. But as a result, all matrices are sparse. All operations are linear scaling, both in terms of time and memory. Okay. There are many, many ways to find K, the density matrix. There are direct methods which do optimization. So the Lieb-Niels-Vanderbilt method, the orbital minimization method. There are iterative methods, the McQueeney method, the TC2 or the SP2 that Anders was talking about. There's divide and conquer that Nakano-sensei was talking about. There's recursion, there's penalty functionals. And of course, there's orbital-free DFT, where we don't know the kinetic energy functional, so we're still struggling there. But that's another way that you can do order n. A word on truncation. There are roughly two approaches to truncation. I've told you about spatial truncation. Once 2 points in space are more than a certain distance apart, we force the matrix to be 0. That's imposing a sparsity pattern on the matrix. We're defining that. The alternative is numerical truncation. Okay, and that's where you do an iterative approach to finding the density matrix, and at every step of the iteration, you throw away elements that are less than a certain threshold. And so there you're imposing a tolerance. Spatial truncation is definitely variational with the range that you're imposing. I don't think numerical truncation is variational with the threshold. The advantage of spatial truncation is it gives you consistent sparsity patterns, which means you can parallelize the matrix multiplies very easily. I have been saying for many years that the numerical truncation gives you varying sparsity patterns, but I had a nice conversation with Anders where he suggested that this may not be the case. So I need to go and read more papers to catch up with my things.
Yeah, you can see it like an equivalence between those two.
Yeah, you can see. Yeah, you can see an equivalence.
What I described in my talk.
Yeah, so the graph patterning is bringing an equivalence.
Yeah, it's two sides of the same.
Yeah. So there are, but roughly speaking, this is how things are kind of laid out. In my experience, this is the physicists and this is the chemists, roughly speaking. It's not always true, but that tends to be the kind of the general background. In CONQUEST, we look at idempotency using the McQueeney function. So this is the McQueeney transform. It's 3x squared minus 2x cubed. And has the advantage that if the input lies between -0.5 and 1.5, then the output lies between 0 and 1. Okay, so if you pass your matrix through this transform, you cluster the eigenvalues around 0 and 1. And so during the course of an optimization, you will have an idempotent density matrix. There are many issues to consider with order n. There's prefactors. There's accuracy. Where do we truncate? But then also, when you're doing diagonalisation, how's your Brillouin zone sampling looking? What information do you require? When you do linear scaling, you do not get the eigenstates. Okay, for linear scaling, you've integrated over the energy. You're working with a density matrix, not the eigenstates, so you lose the energy resolution. You can get it back out again using Lanczos type approaches for a certain window. That's true, but you do just generally lose the eigenstates. You do have to think about parallelization, and you do have to think about timescales. How long do you want to run for? How hard is it to get to the ground state? Let me show you just some brief applications. So coming back to the lead titanate, this was published in PRL a little over a year ago, sort of about a year and a half ago, but it was really nice. So this is the final paper from one of my PhD students' degree work. And we sent it to PRL, and it came back with 2 referee reports, both of which said, it's nice work, but it's not interesting. Okay, this is the kiss of death from PRL, right? So Jack was really disappointed at this point. It was his final crowning piece of work. He said, let's fight this. So we wrote a careful letter, sent it back to PRL, and they agreed. Okay, and I want to find out who those referees were and use them for every other paper that I submit, because I've never had this happen. So it was just really nice that he'd worked incredibly hard for 4 years, and we managed to persuade them this was actually genuinely interesting. So here's what's going on. Again, you've got lead titanate, and experimentally, people have looked at scratches and trenches on the surface of lead titanate, and there seems to be some kind of correlation between the domain walls and the surface trenches. Okay, so the question is why? Why do you find the domain walls between different areas of polarization on the surface near the trenches? And so what we've done is we've taken a PTO film. This is slightly embarrassing. So we went up to 5,000 atoms with order n, but he didn't want to include the substrate because it would make it too big. I was kind of like, come on, Jack, 5,000 atoms is not big. But it was mainly because it was towards the very, very end of his PhD, and he wanted to get those calculations done as soon as he could. Something I haven't mentioned that is a real problem for order n and structural relaxation is that as you go to bigger systems, of course, you get longer and longer length scales. And so it can take longer to relax your system. And this is a problem that's been touched on once or twice over the last 2 decades, but I've not seen a proper answer to this. So this is an interesting question. And if there's anybody here who's got kind of insight into how you deal with these kind of long wavelength, the very slow relaxation modes in structural optimization, that would be fascinating. Maybe I should just kind of forget about structural relaxation and do free energies. Because when you're doing MD, you don't care about the relaxation. You just let it go. Anyway, so we're doing these calculations. We're taking a thick film and we're making a trench, and then we're relaxing it. And we're putting the trenches in various different places, either on top of a domain wall or between the domain walls or perpendicular to a domain wall. And then we're just calculating the energy and the structure. And the headline is that the most stable structure is having the domain wall parallel to the domain centroid, so down the middle of the domain. And if you look at this, you can see what's going on here. So here's a plot. This is a plot of the material without a trench, and this is a plot of the material with a trench. This is here for this is for the domain centroid. This is for the domain wall. And if you look carefully here at these local polarization vectors and compare to the trenched version and the non-trenched version, what you see is that when we put the trench above the domain centroid, so that's the middle of the domain, there's not a huge change in the local polarization. Whereas down here, where we're putting the trench above the domain wall, a lot of these polarization vectors change. And that seems to be fundamentally what's going on here, is that essentially the polar texture in the domain centroid can adapt to the trench, whereas it can't under the domain wall, and that's what drives the location of the domains relative to the trenches or the scratches. And that's not something that you could have done with an experiment. It's not something you could have done with a system that was much smaller than about 5,000 atoms. Because what I haven't shown you here is that actually, as well as the ferroelectric distortions, we've also got titanium TiO6 octahedra, which rotate anti-parallel in every direction. So there are there's a depth here going into the screen. You need to capture all of that as well. Other things that we've looked at include heteroepitaxy, so germanium on silicon. This is something I started during my PhD, and I'm still very interested in. And what you see with germanium is that you put germanium on silicon, there's a 4% lattice mismatch. And so there's a huge strain. And after you put about 3 monolayers down, you suddenly get a transition from flattish growth with trenches to this, where you've got these kind of, it looks like a house seen from above. They're called hut clusters, so they're these big things. And the key question still is it driven by kinetics or by energetics? Is it kinetic or thermodynamic? So here's another picture. And so we're doing these calculations of germanium on silicon. They're mainly done in Japan. So this is a 200,000 atom system, and we actually managed to do structural relaxation on it. It wasn't quick, it wasn't easy, but they did relax it. And so what they're doing now is they're looking at how these things would actually increase. So you're putting new pairs of atoms, new dimers on all the different places on the facets and calculating the energy. And when you do that, you can make plots like this where you can see the change in energy relative to one particular location of putting a new pair of atoms anywhere on the surface. And that's enabling us to think about the growth mechanism. And fundamentally what it seems to be is there seems to be a nucleus here at the top of the facet, and then it spreads down very quickly. I mentioned that you can back out electronic structure from order n. This is using a technique called the Sakurai-Sugiura method. It's a bit like a folded eigenspectrum method, generally where you're pulling out specific states. But what we've done here is we've plotted the charge density for states within 0.01 eV of the Fermi level in one of these huts. And maybe not surprisingly, you see that it's largely confined to the hut itself, which is where most of the strain is. Okay, so that's just showing that you can do that kind of a calculation. We can do MD. We use the extended Lagrangian Bondhop and Homodynamics, which is very nice. It means that you're doing everything correctly and properly. This is just a very simple calculation that Tsuyoshi has done looking at core shell nanowires, so comparing the silicon germanium, where germanium is in the core, or germanium silicon, where silicon is in the core, and heating them to 3000 K. And what we see here is that in both cases, the germanium melts, and the silicon doesn't, or the germanium certainly melts first. It's not surprising, it's got a lower melting temperature, but it's interesting that it melts first, even though it is in a different location and a very different structure in both cases. We can do NPT, just to mention that, though if you're interested, talk to me about stress and linear scaling, because that's an interesting problem. So I'm pretty much done, I think. So to conclude, I've shown you large-scale DFT with CONQUEST, where we do up to 1,000 atoms with no restrictions. We can do up to 10,000 atoms if we're using these multi-site support functions, and we've done up to 1 million atoms with order n. So far, that's only limited by the machine size. You want to go bigger, you just need more cores, fundamentally. And I've shown you, in passing, application of DFT to these PTO films. I showed that the basis sets make a good comparison to converged plane waves. I've shown you these polar domains and the way that the domains interact with trenches. I must acknowledge various people. I don't know how many people remember Mike Gillen, but he gave me my first job. I worked with him ever since. He originated CONQUEST. He's now happily retired, but he was the kind of the inspiration for this whole project. Tsuyoshi Miyazaki and I lead the CONQUEST program, and it was a great joy in December to be able to go back to Japan for the first time in 3 years. Various students and postdocs done calculations on the PAOs. Ayako Nakata was the person who ignored me saying that multi-sites weren't worth doing and went ahead and did them and proved me completely wrong. She's a key part of the CONQUEST development team. And Jack Baker is the PhD student who did all of the PTO-STO work. So I'll leave you with some references, including the CONQUEST GitHub page, and thank you for your attention.